This call is now being recorded.
Good evening, everyone. Today is class 7th of the Aksharamaala initiative. I'll be continuing the electricity chapter from where I left in class 6th. In last class, we studied Ohm's law. Ohm's law was basically the relationship between the voltage across the conductor and current through it. Or you can also say the voltage supplied to the circuit and current through the circuit. So there was a direct relationship. That is, if V increases, then I increases, or if I increases, then V increases. If I decreases, V decreases. So remove the proportionality constant, we introduced a constant which we call resistance, and this relation V equals to IR is known as Ohm's law. Today we will do some numerical problems. This was the first question I was discussing. How much current will an electric bulb draw from a 220 volt source if the resistance of the bulb filament is 1200 ohm? So A part is given to us that there is a bulb and the voltage source applied across it is 220 volt. So how much current will pass through the circuit if the switch is closed? So it is easy to do. We can simply apply Ohm's law, that is V equals to IR. We are provided with two quantities, that is V and R, and calculate I. So I can be calculated as follows: I equals to V by R, and put the value of V, that is 220 volt, and R, that is 1200 ohm. We get this value 11 by 60 ampere, or you can further solve it to 0.1833 ampere using some calculator or maybe some by maths. B part is how much current will an electric heated coil draw from a 220 volt source if resistance of a heater is 100 ohm? Source is again 220 volt. This time the device is a heater, and we don't have to worry about that because we are only interested in the resistance, that is 100 ohm. Previously it was 1200 ohm. So same formula again we can use, that is the Ohm's law, V equals to IR, which again implies I equals to V by R, and put the values of V and R in this formula, and we get I, that is 2.2 ampere. So we can see for 1200 ohm the current was 0.1833 ampere, and for the electric heater, that is 100 ohm device, current came out to be 2.2 ampere. For the same voltage source, lower resistance has greater current value, and higher resistance have lower current value. Because V is fixed, so IR is fixed, that is a constant, and I will be inversely proportional to R. You can see it in that way. Yeah. I equals to constant by R. Removing the constant, we introduce a proportionality symbol. I is proportional to 1 by R, or I is inversely proportional to R, which is basically the Ohm's law for fixed voltage. Let's move on to next question. The potential difference between the terminals of an electric heater is 60 volt. When it draws a current of 4 ampere from the source, what current will the heater draw if the potential difference is increased to 120 volt? So what is given to us is that potential difference between the terminals of heater is 60 volt, and it draws current of 4 ampere during that time when voltage is 60 volt. Say it has some resistance R, whose value we don't know. Now they have asked that what current will the heater draw if the potential difference is increased to 120 volt, that is for V equals to 120 volt if we change the supply. So put it as V1 I1, that is current corresponding to 60. Let's say it's I2 V2. So using Ohm's law, that is V equals to IR. From here we can have two cases, that is V1 will be equal to I1 times R, and second case also will follow the Ohm's law, V2 equals to I2 by R. R will be same in both cases as the device is not changing, only the source voltage is changing. So R1 and R2 will be same. So we only put R and no subscripts. Let's say this is equation 1, this is equation 2. Dividing 1 by 2, we have V1 by V2 is equal to I1 by R upon I2 by R. Divide the right hand side by right hand side and left hand side by left hand sides. That is how we divide two equations. R is same, so it cancels out, and we are left with V1 by V2 equals to I1 by I2. We have V1, I1, V2, and we need to find I2. So from here we have I2, say this, it goes this side. Sorry, there's a call in between. I2 goes to this side and V2 comes to this side and V1 also comes to this side. So now substitute the values of I1, V2 and V1 in it. V1 is 60 volt, I1 is 4 ampere. And V2, it's also given, that is 120 volt. See on the 62s and I2, it comes out to be 8 ampere. So for 120 volt power supply, our device is a heater. Heater will draw a current of 8 ampere from the source. That is this 120 power volt supply. This is our answer. Let's bring the other question. This is our next question. Resistance of a metal wire of length 1 meter is 26 ohm at 20 degrees Celsius. If the diameter of the wire is 0.3 millimeter, what will be the resistivity of the metal at that temperature? So let's write what is given to us. Resistance of a metal wire of length 1 meter. So length is 1 meter and resistance of this wire is 26 ohm, and we are given with the temperature also. If the diameter is given to us, say D is the symbol for diameter for now, 0.3 millimeter. What will be the resistivity of the metal at that temperature? So we are asked to find the resistivity at this same temperature only. Using the table 12.2, predict the material of the wire also. Once we get the value of rho, we have to check also that which material has this much value. Okay, so formula for resistance is R is equal to rho times L by A. So from here we can get rho as A will go to the up and L will go to the denominator, R A by L. So resistivity can be written as 26 ohm into the area. What will be the area of cross section of the wire with D equals to 0.3 mm? We know area of cross section of a circle, that is a cross section of wire, will be pi r square, and the radius is half of diameter. So in terms of diameter, the area becomes pi d square by 4. It is pi by 4 into d square, and d is 0.3 millimeter. You have to convert it into SI because other units are in SI, and all the quantities should have SI unit numbers. So it is nothing else but 0.3. Milli is 10 to power minus 3 meter. Or we can write it as 3 into 10 to power minus 4 meter. Just shifting this to one side, one right side, and put another number in this 3. So that is 3 into 10 to power minus 4 meter. And there is a square also. So A becomes pi by 4 times 9. 3 square is 9. 10 to power minus 4 is 10 to power minus 8. So this much is the area. 9 pi by 4 into 10 to power minus 8 square meter. And the length of this wire is given as 1 meter. This implies that resistivity is 183.78317 into 10 to power minus 8. And the units are ohm meter. Length 1 m cancels out from square meter, and we are left with ohm meter. Dimensionality. Shift this point to two left hand sides, and this will reduce it by or increase it by 2, so 10 to power minus 6 ohm meter. This is one answer, and we have to check also the material. So we will go to the table 12.2, which we saw in last class. Here it is. So our answer for this question is 1.837817 10 to power minus 6. 1.837 10 to power minus 6, this one. It has the value of 1.84 10 to power minus 6. That is the manganese. Okay, no, no. So our material is manganese. Manganese. Symbol is Mn. The atomic number is 25. Let's move on to next question. Next question is a wire of given material having length L and area of cross section A has a resistance of 4 ohms. So we are given that we have a wire whose length is L and this area of cross section, this one, this circle, this is A, and this has a resistance of 4 ohm. What would be the resistance of another wire of the same material having length L by 2 and area of cross section 2A? Okay, so we are asked with we are asked that what is the resistance if the length becomes L by 2 and area becomes twice of the initial area. It's simple. From this first part we apply the formula of resistance and we get the value, that is 4 ohm is equal to rho into L by A. This is equation 1. From second part we have R is equal to rho L prime R prime by A prime. Since the material is same, here they have said that same material. Same material means the nature of the wire, that is conductor, is same. So resistivity for both the cases will be same because we have same material only. Only the physical orientation has changed, that is the length of the wire and the area of cross section. So R prime becomes rho into, now L prime is L by 2 and A prime is 2A. So this becomes R prime is equal to rho L by 4A. From here we can see that rho L by A is equal to 4. This much portion. So using 1, R prime becomes 4 and there is a 4 here also. So 4 by 4 it becomes 1 ohm. This is the new resistance. Now on to the next question. On what factors, the question number 1 is that on what factors does the resistance of a conductor depends? So formula of resistance is rho R by LA. So here there are 3 factors. Rho, that is resistivity, so nature of material out of which the wire is made. Second, the physical parameters of wire. And especially 2 parameters, that is the length of the wire basically it's conductor, so it should be wire, length of the conductor and area of the conductor. And also the temperature The resistance of a conductor varies with the temperature. So for constant temperature only, the resistance will remain constant. This is one important condition. Otherwise, for conductor, the resistance decreases as temperature increases. Second question is, will current flow more easily through a thick wire or a thin wire of the same material when connected to the same source? Why? Solution to, will current flow from, yes. Will the current flow more easily through a thick wire or a thin wire? So we have two wires. One of them is thicker than the other one. That is, the area of cross section is greater. Say the area of cross section here is A prime and here is A. So thicker wire will have greater cross sectional area. Now they have asked that from which one the current flows more easily of same material when connected to the same source. Now if the length of these two wires it is the same, then the resistance of the wires will solely depend upon the area of cross section. Why? Because L is same material means rho is same. So rho L is a constant. So proportionality is R and A, inverse relation. So obviously the greater or the thicker wire, that is the greater cross section, will have low resistance. So current will flow more easily through the thicker wire. But if the L is not same for the two wires, which is not given in the question, they haven't said anything about the length, only the cross section. It is a thick wire or thin wire of same material. There is no condition for the length. So if they have a different length, like this, A prime, A, let's say this is A and A prime is twice, that is this wire is twice as thick as the initial one, and length is L, and say the length is 2L. So if we calculate the resistance R rho by LA, and for this R prime is equal to rho L prime by A prime is equal to rho twice of L twice of A is equal to rho L by A. So the resistance comes out to be same for the both of them. In this case, the current will flow easily from neither of them. It will flow with equal easiness with through the both conductors, as both of them has same resistance. So current will flow through them equally likely. The current will see the conductor, both conductors as same in terms of flow of charge. And if let's say the length of the thinner conductor, it is reduced further. Let's say the length is L by 2, and for the thick conductor it remains the same. Area is A, area is 2A. For the thicker wire it is always greater, the cross section. Length we can change because there is nothing given about it. And still 2L. So R prime will be same as before, that is rho L by A, and R changes as rho L by 2 by A, that is rho L by 2A. So for the thinner wire here, the resistance comes out to be R prime by 2, because rho L by A is the resistance of the thick wire, that is this one. So we see that Even the thinner wire can have lower resistance depending upon the length of the two conductors. So in this case, this will have more easy path for the current. In this case, both of them. And for same length, the thick wire. And if we increase the length of the thin conductor greater than L, it is easily visible. That is, for L it is rho L by A. For the L is rho L by A, and for greater length, the resistance will be some say x times L by A. X is the ratio of the length of conductor with L, so it will be x times R. But it will increase with length only. These are the sub cases. You can take them as sub cases. So now third question. Let the resistance of an electrical component remain constant while the potential difference across the two ends of the component decreases to half of its former value. What changes will occur in the current through it? Let us see what is given to us. Resistance of electrical component remains same constant through a circuit. So let's draw a circuit. Say this much will be fine. And let's say the resistance is R and it remains constant. It is given to us. R is equal to constant. While the potential difference across the two ends of the component decreases to half of its former value. There are two cases. Let's say in first case, the potential difference is V, and in case 2, it is provided that the potential difference across the ends of the component decreases to half of its former value. Former means the earlier value it had, the past value. So here the past value is the value of case 1, that is V. So half means 1 by 2 of V, that is half of V. What change will occur in the current through it? So current can be calculated using Ohm's law and will be I is equal to V by R. So voltage source is V, so we let it be V, and resistance is R, so this is the current. Now they say that what if the potential becomes half of its former value? What will be the current now? So current in case 2, let's denote with I1 and I2. So it will be V by 2 by R. R is same, potential drops to half, so V by 2R, and V by R is nothing but I1, so it becomes I1 by 2. If the potential drops to half of its former value, then current will also drop to half of its former value, provided that the resistance of the electrical component remains constant. This is the answer. Now the fourth question. Fourth question is, why are coils of electric toasters and electric irons made of an alloy rather than a pure metal? So the answer is simple. The electric toasters and electric irons, what are their primary use? Their primary use is to, for the toaster, it's to cook food or toast the bread, and iron is to iron the clothes with high temperature. So basically to become of high temperature, that is to get heated. That is the principal function of these two devices. That is to generate high heat so that we can cook our food or iron our clothes. So for high heat, we need high melting point. High melting point, or which is the greater advantage, is that high oxidizing point of metal. That is the burning point. And for the alloys, the oxidation it occurs at a very high temperature as compared to the metals, pure metals. So they do not burn easily. The alloys do not burn easily and can achieve higher amount of heats. Greater amounts of heat. So we can generate high amount of heat and our material will also not burn. So that's why alloys are used over the pure metal for heating purposes. Next question. Use the data in table 12.2 to answer the following. Which among the iron and mercury is better conductor? Let's quickly grab the 12.2 table. So it is asked that which among iron and mercury is a better conductor. Better conductor means it will produce less resistance for the same physical parameters of two conductors. One will have a lower resistance, that one will be the better conductor because it will allow easy flow of charges over the other. So let's quickly find out iron here and mercury. So iron has a resistivity of 10 into 10 to power minus 10 and mercury has 94 into 10 to power minus 8. So resistivity of iron is less than resistivity of mercury. So iron will be a better conductor over mercury because for same physical parameters, that is when L and A are constant, so R is proportional to rho. So for lower iron, lower resistivity, resistance will be also lower, and that is the meaning of a good conductor. Low resistivity. So here, iron is the answer. Which material is the best conductor? So from this table, the one with the lowest resistivity will be the best conductor, which is silver here. Silver with the resistivity of 1.60 into 10 to power minus 8 ohm meter. So we have some time left. Let's continue with the next topic. That is resistors combination. Let We write it other way around. Combination of resistors. We have two fundamental combination of resistors. One of them is called series combination, and the other is called parallel combination. What is the meaning of series combination is that the terminals of the resistors are joined end to end with the adjacent resistors. That is, in a series simply means one after the other in a line. So say it's the first resistance R1, then there will be another resistance R2, then any number of resistances you want. When this is joined from one end of a resistor to the other end of other resistor, and so on. This is a resistance series combination. In case of parallel combination, the ends of the resistances are joined at a common point. Suppose this is one resistance, this is another resistance. All these terminals or one end of the resistor will be joined to this common point, and similarly for the other terminals at this common point. So this is a parallel combination. Now let's study them in detail. What will be the net resistance if we have such combination? Suppose this one, if we apply a potential difference of V volt, then it will produce some current for closed circuit. It will flow like this, go through the first resistor, and it will go to second, then third, and come back. So this will be the direction of current. It will remain I throughout the circuit as there is no splitting in wires. Splitting means this circuit here, the parallel one. Here the wire splits into three. Not splits, or it diverges into three channels, you can say. So here the current is same through the circuit. Now consider this circuit to be as a single resistor circuit denoted by RS. S simply means series. Nothing much to remember. So the net resistance of this circuit, that is RS, will be as if between these two terminals A and B there was only one resistance, one resistor of that value RS, instead of this multiple combination of multiple resistors. There will be only one resistance. That is the net resistance. That is the definition of net resistance, you can say. That is, if we replace the whole combination with a single resistor, then the value of resistance for it will be the net resistance of the system. So in this one, we can simply apply Ohm's law. V is equal to IRS, and I equals to V by RS. Okay. So the current will be voltage upon the total resistance. Now in this circuit, this one, let me quickly grab it also. Oops. So in this one there is current I, and current value I is given as V by Rs. So potential drop across this one resistance, let's say it is V1, across this resistance, let's say it's V2, and across this resistance, let's say it's V3. Let me redraw this one. From A to the next point. This material will not have any resistance because it's a ideal wire. Across R1 is V1. So Ohm's law will apply to each resistor also. That is V equals to IR1. Current is same through all resistances. V2 equals to IR2 and V3 is equal to IR3. And we don't even need this current. There's a simpler way. The simple in series resistances, the voltage is divided across the components. You simply see the V voltage is being divided across these three resistors as V1, V2 and V3, but total potential will remain the same. It is V. So V1 plus V2 plus V3, it must be equal to V. Here we can apply the Ohm's law again, or just let me rephrase it. Just put this equation 1 and these three equations. Let's say it is equation 2 in 3. Put 1 and 2 in 3. So it becomes IR1, that is V1 plus IR2 plus IR3. I'm just putting this one here. V1 here, V2 here and V3 here, and V will be here. Equals to IRS. Take I as common. I cancels out on both sides. And we are left with series resistance of R1 plus R2 plus R3. This is the formula for net series resistance. Or you can say net resistance of a combination of resistors in series. The other one is the parallel combination. Actually, I have a better diagram. Okay, so this one is the parallel combination. In this one, you see that the terminals of the resistances are joined to one common point on both sides. Such combination is called parallel combination. And when the current flows through this circuit, at this point it splits into three parts. And the potential, it will remain same across all three resistances because they are in parallel combination. The potential will not divide because potential drops across two terminals in parallel combination. voltage across resistance, voltage across resistors, what remains, it is same. Current through resistors is different. Why? Because voltage is something that we measure across, that is across the terminals. So if I put a potential or the voltmeter here, then I get some value. Then I have to calculate for R2. The terminals are again same, so we get same value. And for R3 also the terminals are same, so we get same value. So same voltage. Current we put ammeter in the three arms differently. So depending upon the resistor value, there will be Ohm's law application and it will give out current. So the current will have values depending upon the resistances. So when we don't know the resistance, we say that the current is different. It is through the resistor. That is why ammeter is connected in series. So the voltage is same across three resistors. So applying Ohm's law gives V equals to, say, I1 is the current through R1. So R1, I1, R1, say current, this current is I1. It goes through R1 and comes back here. I2 and I3. I2 and I3. So we have this node. Here are the resistances. So current I splits into three parts. So the equation which comes from here is simple. It is I equal to this splitted parts. The splitted parts will constitute the whole current. So V is I1 R1, V is I2 R2, and V is I3 R3. So from this one we have I1 is equal to V by R1, I2 equals to V by R2, and I3 is equal to V by R3. It is lagging a little bit. Let me quickly check. Oh, I stopped presenting only. Yep, recording is still going on. Hello. Yes. So let's continue. Yes, this one we were here. So current through these three resistors is I1, I2, and I3. We put them in this equation. From where we got this equation is simple, that if I is splitting into some components, then the sum of components will give back us I. So we have total current is equal to V by R1 plus V by R2 plus V by R3. Remember, in the case of series, the voltage is divided, current remains same. Through all the resistors. So we add voltages because voltage is divided. And in case of parallel combination, the current is divided or say different. Voltage is same, so we are adding currents this time. Now consider this whole circuit. This whole circuit is equivalent to this one circuit. This RP this single net resistance RP component, it is equivalent to these three resistors in parallel combination. It is the R1, R2 and R3. So net resistance, how will we calculate it? Simple. Apply Ohm's law. Wherever you see voltage and resistance, just apply Ohm's law. You will get one value out of the three. I equals to V by RP. Now say this is equation 1 and this is equation 2. Put 2 in 1, 1 in 2 or compare 1 and 2, anything. We get V by RP equals to V by R1 plus V by R2 plus V by R3. V is common, cancels out. We are left with 1 by Rp equals to 1 by R1, 1 by R2 plus 1 by R3. This is the net resistance for parallel combination or net resistance for the resistors arranged in a parallel combination. So for series, we see that the net resistance is simply a addition, and n number of resistors are there, then up to Rn. Just add all the resistance values. For parallel, we see the reciprocal of net resistance is equal to summation of the reciprocal of each resistance up to nth value. First we calculate this thing, then we again take a reciprocal, so we'll get a net resistance. So it will look something like this. N values Rn. Let's do an example for this. Question is an electric lamp whose resistance is 20 ohm and a conductor of 4 ohm resistance are connected to a 6-volt battery. Calculate the total resistance of the circuit, the current through the circuit and the potential difference across electric lamp conductor. In this one only series combination is there, the parallel is not there. It's not a good example actually. Let me see some other questions. Okay. Yeah, this one is good enough. This is the question. In a circuit diagram given in figure 12.10, suppose the resistance R1, R2, R3 have values 5, 10, 30 respectively. This is R1, this is R2, and this is R3, which have been connected to a battery of 12 volt. Calculate the current through each resistor and the total current in the circuit. The total circuit resistance is, so A part is current through each resistor. So first we need to find the value of this. No, not exactly. Given voltage is 12 volt, so current through each resistor will simply be I is equal to V by Ri. So current through R1 is, say I1 is equal to V by R1. So it will be simply 12 by 5 ampere. Current through second resistor will be similarly V by R2, and I3 is V by R3. This is 12 by 10, 1.2 ampere, 2.4 ampere, and I3 is 12 by 30. So 3 ones are 3, 4, then there is a 10, so 0.4 ampere. B part is total current in the circuit. Total current will be summation of all these three currents. That is 2.4 plus 1.2 plus 0.4. 3.6 and 0.4, that is 4 ampere. This is the answer of B part. This is the answer of A part. C part is the total circuit resistance. Since it is a parallel combination and the values are 5 ohm, 10 ohm and 30 ohm. This one. So net resistance we know will be the reciprocal will be the sum of reciprocals of all individual resistances. So 1 by Rp equals 1 by R1, that is 5, 10, 30. How we solve it? Take LCM, which will be 30 itself, 35, so 6, 30 by 10, 3, 30 by 30 is 1. So Rp becomes 6 plus 3 plus 1, 10 by 30. This is 1 by Rp actually. So 1 by Rp is 1 by 3. And take inverse on both sides, it becomes Rp is equal to 3. Right, 3 ohm. Simply let me give an example for series. If I apply or connect these three resistor only in series combination, just extending the question. R1 is 5 ohm, R2 is 10 ohm, and R3 is 30 ohm. So net resistance of the series will be, which we saw is the summation of all the resistances in series. So R1 plus R2 plus R3. So series resistance becomes 5 plus 10 plus 30. That is 15 plus 30 is 45 ohm. We'll do some good examples next time also, for series also and parallel also. So these were the combinations. Let me quickly summarize what we studied. It's some numericals on Ohm's law. Second, series and parallel combination of resistors. In series, the resistance just keep on adding. In parallel, the reciprocal of the net resistance is given by the summation of or the sum of the reciprocals of individual resistances. In series, the voltage is divided into components. I is same. Voltage is divided. In parallel, the current is divided. Into components. Number of arms, number of components. And voltage is same. And we did some example for the second point. Second point, numericals. What is this one? That is all for today. Thanks for watching. And as usual, if you have any doubts, put it on the WhatsApp group or the Aksharamaala platform from where you have logged in as a student.